So this should be a short video. I wanted to put forth my best, most simplest. Is it most simplest? The easiest explanation I can give. The gist of the argument is that the cosmological redshift that cosmology has discovered, the Hubble redshift, it's this distance relative redshift in distant stars and galaxies that shows that the universe is expanding. They just extrapolate and say it's the Doppler effect. They're like, oh, the light's redshifted, so it's expanding. And that's basically the assumption. General relativity does not predict this. General relativity allows this to happen. Okay, this is not a prediction of general relativity. This is just allowed by general relativity. There's lots of things that can happen with general relativity. The universe can collapse. It can expand. Obviously, galaxies and stars do this all the time. Anyways, so the argument here is that the observer, which is right here on the outside, the right side of the purple circle, the observer here is at a place where there is very little gravity. And in all of these experiments that we're about to perform, the observer is at the lowest point in the universe, the part of the universe that we can find the lowest amount of gravity, the lowest amount of mass, the least dense. There is basically nothing here. This is a void, okay? And so we're trying to eliminate as much gravitational blue shift as possible. Because cosmologists say that there is a counteracting blue shift. So we're just going to place a small, tiny, little bitty observer in a void. And there's no gravity here, okay? Sorry, that's repetitive. But the emitting star is going to be a very dense star, okay? It's very dense. It's not well. It doesn't have to be dense. It's very massive. And it's in a massive galaxy, which is in a massive cluster in a massive region of the universe. Okay, so this is the most amount of gravitational redshift that you can have. Well, not the most, but we're talking about a significant amount just between the observer and the emitting star. And so my claim is that you have to include this other stuff. Like, what is all this other stuff? So we talked about the galaxy, but that's a little bitty tiny thing right here. Like, what about all this stuff around it? So that adds to the gravitational redshift. What about everything else? Does that add to the blue shift or to the red shift? I mean, I just say that it all adds to the redshift. Like, it would all go that direction. Does this make sense to anyone? Like, you have to draw the boundary somewhere. Regardless, so if you do the calculations, this is for 101 megaparsecs, which is this many light years, this many meters. This is the Schwarzschild radius. This is the amount of mass, okay? This is the mass density. And this is the gravitational acceleration. So the gravitational acceleration is going to be what stays the same. That's going to be kind of the deciding factor for this model. Okay? So when you're modeling the universe, like when you're doing, this is a calculator basically that's modeling the universe kind of. Like it's just inputting the parameters here based on this. And so I'm going to increase the distance between the observer and the emitting star. And the amount of mass increases. And so, this is the gravitational redshift. Hopefully y'all can see this, where I'll have to go back and add arrows if you can't see where I'm highlighting. But regardless, I feel like this is just self-explanatory. I don't know what else to say. All of the mass goes to the emitting side. And so in the equation, so this is the gravitational redshift equation. Usually you would have the observer up here, but we're in a place that's basically 0, so it's 1 minus 0. And so it just reduces to 1. And so this is how it just reduces. And so that's the gravitational redshift. When you do this, you can always come up with the Hubble parameter. Now I can adjust the Hubble parameter here, and it'll make the adjustments. See, the gravitational acceleration changes. So I've fine-tuned it to be at 72. That's about what my assumption is. I mean, it could be something else, but this gets bigger. You know, we can make this really big. It goes so as you're getting more out there, the total redshift gets larger. The amount of gravitational redshift gets ridiculous. And so this is from recession velocity. This is just for a comparative thing. It's going to be the exact same thing as the gravitational redshift. So this is if you're expanding. This is if you're not expanding. If you're expanding, you should also have the gravitational redshift. And so it depends on the mass density, and there's a lot of fine tuning in there. But I am basing this 3.5 gravitational acceleration based off of some critical density estimates as you get higher. So the mass density in this model is inversely proportional to the radius here, the distance between the emitting star and the observer. And the reason is because the gravitational acceleration is relatively uniform. And so it's relatively uniform is the wrong way to say it, but it's a good way to explain it, kind of, I guess. But it's more of a minimum gravitational acceleration. So even at this point where the observer is, it's going to be this gravitational acceleration. I mean, the reason is because it's there's the mass density is distributed relatively evenly on each scale. So while mass density is inversely proportional to the radius for each scale, so for all things that are 1 megaparsec in diameter, they're going to have about the same amount of mass density. It's just the larger scales have a lower mass density and the smaller scales have a higher mass density. But the gravitational acceleration stays about the same. Regardless, if you count it to all going towards the emitting side, you can come up with a Hubble parameter. I'm not the best explainer. Like, I shouldn't be making YouTube videos. I don't know why you're listening to me. I am the worst person ever to listen to. But I mean, I taught myself, and so like I can't hardly explain what I'm. Like, I have to take my time, and so when I press the record button, my mind just goes blank. And like, it would be better, I guess, if you could ask questions. I may do a live session and just have question and answers. There'll be nobody that would show up though. Regardless, I wanted to show you this gets weird around 4160, around 1300, 13.57 light years. So this is 4160 with the Hubble parameter at 72. So this is the redshift is equivalent to this. The universe is not expanding. The redshift is just equivalent to that. So the emitted versus the observed. Gravitational redshift, you can see here we're at 33.17. That's ridiculous. And so as you go up, it goes up too. Look at the Schwarzschild radius though. See, typically the Schwarzschild radius is much, much smaller than the radius, the distance, the travel distance. But as you get more and more, or as the radius increases, the Schwarzschild radius increases, and it surpasses here. Well, at some point, really soon, it surpasses. It does. It surpasses right here. They're the same, but I don't think I can calculate more. Yeah, it surpasses right there. See, I thought it would nan on me. Nan. Regardless. That's how I come up with the cosmic microwave background radiation. It's because the universe is a black hole. The Schwarzschild radius, if you don't know, is the radius of an object if it was a black hole. So the Schwarzschild radius of the universe is the observable radius. Which is okay. So that means that there's going to be Hawking radiation, or it's basically just the Unruh effect. I don't really know which you would call it, because it's not really Hawking radiation, but it's very similar. I mean, you use the same, use the exact same equation. Another interesting thing here is the collapse time. So a lot of people say that the universe is unstable. It is unstable. If a static universe would collapse in on itself. But if you just look, the collapse time increases as the radius increases. So, in other words, the bigger it is, the longer it takes to collapse. And this right here is much more than the amount of time, like the amount of time that it would take for light to travel across to reach us. Like, it's a ridiculous. The collapse time gets absurdly large, so it's not going to collapse. Now, there's portions of the universe that would collapse, because there's certain portions that are collapsing right now. It just depends, because a smaller radius is a smaller collapse time. This really only works for distances greater than 1 megaparsec or so. Much better. It gets more accurate the larger the scale, or the further the distance. You can visit this if you want and check it out. I'll put a link there. It doesn't work on mobile. It's terrible on mobile. So be wary of that. I don't know. And this should all be accurate. I have looked over it and painstakingly went through the JavaScript. It was quite a project for me, honestly. This was a project for me, but it's done now, and whatever. Anyways, that's my best argument. What do you think? I mean, I hope this makes so much sense to me. I don't know what everybody else just is like, you're a pseudoscientist crazy nut job, and I'm like, though, this is the simplest, easiest thing in the world. Why is the universe expanding? Like, the universe doesn't have to be expanding. It's just gravitational redshift. What are you guys talking about? Like, all of the mass goes to the observer, because the emitting star, is more massive than Earth, so it's all already a redshift. And so there's, I think it's Birkhoff's. Is it Birkhoff? Is that right? Birkhoff's theorem? I should have looked that up and wrote it down first. Basically, it's the Newtonian shell theorem. It's just that's in general relativity, the version. And so it's, you know, I mean, this is just basic gravity, in my opinion. I don't know why cosmologists think differently. And it's because, the reason is because this is what they did back in 1920, and they've just stuck with it. They haven't changed because they're too scared. Because we're talking about Einstein was saying this stuff. Like, I mean, Einstein wasn't saying this stuff at first. I mean, he eventually agreed with people, I guess. But, like, he argued with them for a long time. He didn't much like it. But, like, he thought like, just like me, the universe is, I don't know. But see, they would say, no, he didn't think about gravitational redshift. I don't know if Einstein even knew about gravitational redshift in the beginning. Like, I don't think that was part of the, now I'm sure it was something in his thoughts, but I don't think it was part of his original package in general relativity. Now it did immediately follow it. Like, it was definitely a prediction, is what I'm saying. But it was always stuff like, not cosmology, gravitational redshift, because they were like, it's so tiny. Like, they just assumed it was tiny. They even calculated it for the sun. And it's like, it's small. It's a small amount. Like, for the sun is like, let me just, point, now this ain't accurate, but let's say 0.002 megaparsecs. See, look, the gravitational redshift is tiny. That's a tiny amount. It's so tiny. And so, that's Einstein's like, it won't do anything. But they didn't think about it adding up, because it's weird to say, like, where do you draw the boundary? Like, a star isn't the end of it. And, the cosmologists argue that it's the point of emission that matters. Well, that's fine. The point of emission is one point, and then okay, where do you draw the boundary? You have to draw the boundary at the observer. You know, the emitting, this is the boundary. This red line is the boundary right here, and this red line right here. This is the boundary. Okay, like this circle is the boundary. This is how you draw the boundary. It's not at the star. Because there's mass on the other side of the star. The star is inside of a galaxy. The galaxy is inside of a cluster. Okay? The cluster is inside of a vein. This vein is part of a network. See, this is all together. This is all one thing. And so this light is having to travel through this thing gravitationally and end up here. As it's traveling, and so like we can just go, you could do thousands of experiments. You could set up a person here, and then a person here, and here, and here, and it's going to all work. The light self-corrects just by traveling. So it's not like it's predicting the future. Like the sphere increases as it's traveling. And the point of observation is where you draw that boundary. Man, I hope I'm making sense. I sound like an idiot sometimes, especially when I press record. And, you know, it's possible I'm just a complete lunatic. That's entirely possible. I don't know. I don't know. Whatever. What do you think? Oh, how long did I go? Oh my goodness, we're at 16, 17 minutes. I was going to try to make a 5-minute video. What the heck? And as far as general relativity goes, I'm going to say this one more thing. As far as general relativity goes, I think that the best way to approach it, as far as cosmology, is that a whole bunch of different solutions exist. The universe isn't doing one thing. It's doing a whole bunch of different things. And so you have to map it all out. And everything's relative. So you can't just assume the universe is a single system, but it's doing a whole bunch of stuff on a whole bunch of different scales that interacts with general relativity much differently. So it's, this is not something that cosmology can conquer with general relativity. It's kind of nonsense, honestly. Like, that's my opinion. Let me know your thoughts.